Ryan Jagannath, and this is my Physics 2212 Lab 5 report. So, the purpose of this lab is to understand Faraday's law better, and to do that, we dropped a bar magnet through a conducting tube of aluminum foil and collected the time data. So, the fundamental principles, the Biot-Savart law for the magnetic field of a moving point charge, Faraday's law for motional EMF, Newton's second law, force equals ma, and then Newton's third law. Results that I got, which I'll go over how, is the experimental average time taken for the magnet to drop through the tube was 1.258 seconds, and the computational model showed that it took 1.247 seconds. So here are the measurements. The length of the tube was 0.33 meters, width of the tube 0.007 meters, the inner radius 0.03 meters, and the total radius is 0.037 meters. The magnetic moment, which was from lab 3, I calculated it to be 2.15 amperes times meters squared. The mass of the magnet is 0.025 kilograms, and then as you can see here from these 5 trials, the time taken for the magnet to fall through the tube, the average was 1.258 seconds. So the experimental tech point questions: why can't we use a ferrous tube, a steel pipe? We can't use it because it contains iron, and this could become an induced magnet, which can then interfere with the falling bar magnet and change the results. And then what happens to the magnet? How can this compare to the magnet falling in free space? When the magnet falls through the tube, it falls through much slower than it would if it would have fallen free space without a tube. I actually tested it out. I don't have it here, but I tested it out, and with free space, in free space, it would probably take only about 0.3 seconds to fall through the same amount of tube length. So this is the computational model here, the glow script model. As you can see, I just put in the values here, and then here we're defining the B field, and then here we're defining magnetic flux. Here we're defining the gravitational force, the net force, and then the velocity of the bar and the position of the bar. And this is what the output showed. So this is what the it looks like with the wire, and then this is the magnet down here. And then this is the velocity versus time graph. As you can see here, it starts off going at a really high velocity. Obviously it's negative because it's going down. And the time taken by the computational model is 1.247 seconds. So what if the resistivity of the conductor were reduced as close as possible to 0? By Ohm's law, I equals V over R, so reducing the resistance almost to 0 would make the current maximized. And since this is an induced EMF problem, the current is the one that's like stopping the magnet from falling quicker. So this would impede the speed of the magnet, and it would make it fall through the tube slower. What if holes or slots were cut into the tube? How does this affect the ring currents? This would reduce the magnetic force, since there would be fewer rings in the tube, and thus the magnet would fall quicker through the tube. And then the source of error, the main source of error that I found is a human error in timing during the experiment. So figuring out some of those values during the trials, that could have been off by a few tenths of a second. So that's it. Thank you.